calibrate and validate the model. He worked for 10 years, he used 6 years for calibration and 4 years for validation. And then for the second session, he gave us introduction about the weather database for FAO, and then he gave us also important lecture about the estimation of ET node reference evapotranspiration and actual evapotranspiration, and how we can calculate the crop factor, which is very important for the calculation. This is just in brief, and today we can start today the session, the third session, and today Dr. Ihab, he is going to give us. He will talk about the irrigation scheduling using AquaCrop software. And please, Dr. Ihab.
Thank you. Good morning, everybody. Just I will reintroduce myself, just in case somebody joined us today. My name is Ahmad. I'm the head of Water Resource Department at ACSAD, and we work under the Arab League. We're based in Damascus, Syria. Yesterday, I talked in detail about how you can use the vapor database to estimate ET0, then how we can get ETC through using ET0 and crop coefficient. The focus today will be on irrigation scheduling and using very important software. It's called AquaCrop. AquaCrop, as I mentioned yesterday, developed by FAO, and I guess one of the best software used for irrigation management. Of course, I mean, during today's presentation is very difficult to cover all details about AquaCrop. Usually, I mean, we need 5 days training course to cover the AquaCrop component, but at least I will try today to give you a very good idea about using AquaCrop for irrigation management. Let me start before go to AquaCrop model, talk about irrigation scheduling in general, I mean, and how we do the irrigation scheduling, I mean, regardless of using the model. I will share my presentation. Can you see it, Dr. Muhammad?
Yes, it is online.
Yes.
Thank you.
Yes, Dr. Ihab.
So I'm talking about irrigation scheduling in general now. As most of you know, I mean, we define total available water in soil, and which is the water between wilting point and field capacity. So total available water in soil is this is the maximum water could be retained in soil, and is soil moisture between wilting point and field capacity time the effective root depths. So I mean, of course, in order to know the total available water, we need to measure the field capacity and wilting point, and we need, very important, we need to know the effective root depths. A lot of engineers, they don't give a lot of focus on effective root depths, but if effective root depths was not correct, everything will be wrong. And effective root depths depend on the plant, of course, and even for the same plant is not the same everywhere, depend on the soil, and if you have hard pan and the bulk density of soil. So really, I mean, we need to get this from the field. for our crop, and it's better not to get it from reference or because it will vary, I mean, from place to place and from variety to variety. Also for field capacity, some people, they do this in the lab. This is not correct. I mean, you have to do it in the field because field capacity is a function of soil structure and texture, both, not only texture. So we have to do it in the field, and the same for wilting point. So we need to know our total available water as first step. There's a lot of reference available around. Even I said you have to get it from the field, but sometime maybe, I mean, just we can find, if we don't have field measurement, maybe you can use some data from the reference, just in case no way to get data from the field. And this example for effective fruit depth for some crop. And this also approximate value for field capacity and wilting point for different soil texture. The second thing, we need to know what we call readily available water. Readily available water is defined as the soil moisture between field capacity and critical moisture. So critical moisture is moisture higher than the wilting point and less than field capacity. So it's somewhere between wilting point and field capacity. So readily available water, this we talk about water, plant can take, absorb easy. There is no stress on the plant. And of course, therefore the critical moisture is different from one plant to another plant. So total available water, this water available to the plant, I mean, theoretically, we can say that the plant, if we start at field capacity, can absorb all moisture until we get to the wilting point. But in fact, we never do that. In irrigation, we allow plant to consume only part of total available water. This part, so is of total available water, we refer to as readily available water. So readily available water is percentage of total available water. This percentage could be 20%, 30%. This percentage we refer to as MAD, management allowed deficit. So how much water we allow for the plant to consume from the total available water before we irrigate again. So MAD, this ratio could different from one plant to another plant, and this depends how much the crop is sensitive to stress. For example, for a crop like potato, we allow only maybe 20 to 30% of total available water to be consumed before we irrigate, because potato is very sensitive to water stress. For cereal more tolerate to stress. So this we allow higher ratio to be consumed. MAD could be 60%. This is very important, I mean, for irrigation engineer to know this. So, I mean, we should know our total available water, but we never, I mean, let the plant consume the whole total available water. We allow only percentage of total available water, so the plant will not be subject to the stress. Because if the plant was subject to stress, then this will affect the yield, and the yield will be reduced. This table shows value of MAD for different crop, and we can see example. For example, for onion, this value 0.3, this is sensitive to water stress. So we allow only 30% of total available water to be consumed by plant before we irrigate and increase the moisture to field capacity again. Let me see if, for example, for cucumber, this ratio is 50%. In general, for vegetable, MAD is about 0.4, for cereal, 0.6. Most engineers, they might use the value of 0.5 if they don't have a reference value. This means, if we start at field capacity, when the plant consume, for vegetable, for example, 40% of total available water, we have to irrigate again. So now the question is, what is the maximum irrigation interval between two irrigation events? So this we can get very easy, because if we divide the readily available water, this amount of water allowed to the plant to be consumed, divide by the daily water consumption, daily ETC, which we talked yesterday about. So readily available water divided by ETC, we can get the maximum irrigation interval between two irrigation events. Of course, this is not fixed for the whole growing season, because ETC is changed from one stage to another stage, from one day to another day. So for every stage, we have different maximum irrigation interval. If is function of root depths, not only soil property, root depths also change during the growing season. So Nmax is not fixed during the whole irrigation growing season, and we have to calculate it for different growing period. So this is the main concept. Of course, the actual irrigation interval could be any value less than the Nmax. You can, it depend on other management factor we can select, but irrigation interval should in no way should be more than Nmax, which calculated from this ratio. So this summarizes the main principle of irrigation interval. So irrigation interval is function of soil property, field capacity, wilting point, and root depth, and of course the weather condition, which ETC is calculated based on it. This quick summary about, and in general, any irrigation management should be based on this concept. Let's have a small example. If our field capacity was 42%, wilting point 23%, the root depth 120 centimeter, and ETC 10 millimeter per day, MAD the ratio 0.5, and you need to find the maximum irrigation interval. So first we calculate total available water. So this is the root depth in millimeter. This field capacity, wilting point. So the answer will be 228 millimeters. So the total available water in my example will be 228. But I mentioned MAD is 0.5. So readily available water is 0.5 times 228. This means even my total available water 228, when the plant consumes 114 millimeter, I have to irrigate and refill the soil to the field capacity. N maximum will be the readily available water, which is 114, divide by 10. And the answer will be 11.4. This means the maximum irrigation interval should be 11 days. But actual irrigation interval could be any number less than 11 days. Okay? So before I continue to talk about AquaCrop, using AquaCrop, maybe I will change a little bit the arrangement today. I would like to allow question for 5 minutes or less about the concept I just talked about. So please, before I continue, because I start to see some question. If you have any question about the main concept of irrigation scheduling.
Dr. Ihab, one question has been posted about what is the famous estimation that gives RAW equal to 2/3 CWW?
Can you, what do you think about the famous estimations that give readily? Yeah. As I mentioned, we cannot fix readily available water, this ratio, because this very much depend on the crop. For olive tree, this ratio could be 0.7, 70%. So I allow plant to consume 70% because olive tree tolerate to water stress. But for vegetable, most of time, this will be 0.3. So really, most of time, maybe we allow to use 0.5, but it's much better to vary this ratio depend on the crop and type of crop. Okay, is there any other question?
Yes, I have a question.
Yes.
Okay,
Yes,
so
introduce yourself, please. Ali Awad.
Yes, I'm from University. So in order to make a comprehensive assessment, what? Is my voice clear now?
Can you repeat? Yeah, please.
Yes. So in order to make an comprehensive understanding between today's presentation and yesterday, so can you correct me if what I'm saying is wrong? When you said that the number of irrigation interval should be less than or equal to the maximum number, I thought that it will be equivalent to the maximum number when the crop in both stages of the initial and the third stage of the I can't remember, the middle stage, I think, while it will be less when we deal with the crop development stage. Is it right? Thank you so much.
Thank you for your question. Exactly what I mean, you are very close to what I was saying. Yesterday I mentioned we have 4 stages. I mean, we have the initial crop development, mid-season, and the end season. So we need to calculate N-max for every stage. And sometimes maybe you calculate for shorter than the whole stage. And N-max, it will be different from one stage to another stage because root depth will increase during the season, and also ETC will change depend on the weather condition. So for every stage, we'll have different N-max. So I don't know if I answered your question.
Yes. So regarding the second stage of the crop development, so only in this stage and the second stage that between the mid stage and final, both these, the N will be changing, which will be less than the N max of the stage itself.
No, I mean, we'll have N max for every stage. For, let's say, you're talking about N max for development stage. This is your question.
Yes,
so,
no. What I meant to say that you said that the actual irrigation interval, it depends on the needed water at that time. Okay, so the required in both the initial and mid stage will be equivalent to the maximum itself, while both in the crop development and and between the mid and the final, the end stage, in both the real interval will be the maximum interval.
Yeah, you are a little bit mixing two things. You're mixing between maximum ETC and maximum irrigation interval. For every stage, there is maximum irrigation interval for every stage. So does not this mean this is the maximum value for N for the whole growing season? So every stage has different N max, because this related to RAW during this stage and ETC during this stage. So every stage have different N max. And so this something different from the maximum ETC or the maximum KC. Okay?
Okay, let me clarify for the last time.
Okay.
For the first value of the maximum irrigation interval in the initial stage, it will be 1 max. Okay, so the really applied, it will be the N1 max itself. Okay, when speaking about the third or the mid stage, it will be for example N3 max, and the really applied, it will be N3 max. But in the crop development, the interval value will vary, and all these value will even be less than or equal to this N max. Thank you so much.
Okay. Yeah, during the development, we'll have N max calculated from RAW during this stage and divide by ETC during this stage. So ETC during this stage will be calculated based on ET0 and KC during this stage. Okay, do you have any other question before I continue? Okay.
Thank you so much.
Okay, you can proceed.
Miss Adam has a question.
Okay.
She posted to the chat. If
Horia?
you'd like to speak.
Is Horia or who?
Exactly.
Yeah.
Fadlan.
Can you open the microphone, Horia? Unmute. Okay. Okay. So the question is to, comparison between AquaCrop and CropWatt. There's complete difference between the methodology used in AquaCrop and the CropWatt. In CropWatt is based on the crop coefficient, and we'll see in AquaCrop we don't use the crop coefficient. And also AquaCrop use daily value, while CropWatt use monthly value. And there's very important things. Unfortunately, AquaCrop cannot be used for tree crop. It used only for field crop. Until now, the model cannot be used for tree, while CropWatt can be used for all crop. But the concept on irrigation management, the way transpiration is calculated and evapotranspiration is different from CropWatt. So maybe after I explain, we can go back to this question. Okay. Is there any other question?
No, it appears not for now. Please proceed.
Okay. Let me talk a little bit first about, we started yesterday talking about reference crop evapotranspiration, and the ET naught is the evapotranspiration rate from reference surface, not short of water, and the reference surface typically is used the hypothetical grass reference crop with this. Hello?
Yes, we can hear you. Please proceed.
Okay, because we lost the connection. Can you see the screen now, Marlene?
Yes, we can see the screen.
Okay, good. And there is different method, I mean, to estimate ET0. Yesterday we talked about using the vapor. This one of the methods that we have the band evaporation, and there are many equations available around can be used to estimate ET0. FAO 56 recommend using FAO Penman-Monteith equation, which it is on the screen now. This very famous equation to estimate ET0, and of course it needs different weather parameter. We need the net radiation. This calculated based on coming radiation, ground energy. We need the temperature. We need wind speed at 2 meters, and ES actual vapor pressure, and ES the saturated vapor pressure, and EA actual vapor pressure. So this is Penman-Monteith, and this is the one used by AquaCrop. Therefore, I'm presenting, and it needs different parameter. ES saturated vapor pressure is calculated based on the temperature, and EA is calculated from ES using relative humidity. So I can use this equation to estimate ET0, but I need incoming solar radiation, I need temperature, I need wind speed, I need relative humidity. I need all these parameters in order to calculate ET0 using Penman-Monteith equation. And wind speed used in this equation should be measured at 2 meters. If it was measured at different height, I can use this equation to convert the wind speed from any height to 2 meter height. Of course, many people make difficulty to make all this data available. I mean, especially maybe many weather stations, they don't have net radiation or wind speed. So, I mean, if you go back to FAO 56, you can see even you don't have all this parameter, you can use Penman-Monteith equation. And so if you don't have relative humidity, so one of the parameters we need in Penman-Monteith, we need relative humidity to calculate actual vapor pressure. There is alternative equation we can use to calculate actual vapor pressure based on minimum temperature. So if I don't have relative humidity, I can still calculate actual actual vapor pressure based on minimum temperature. If we don't have incoming solar radiation, we can calculate this from this equation based on maximum temperature and minimum temperature. So we need measurement of minimum temperature and maximum temperature. And of course, we have RA. This is atmospheric. This I need to correct this atmospheric solar radiation, and this we can get it from table based on latitude and the months we measure the ET. So we can use this equation. We can use this equation to estimate incoming solar radiation. If we don't have wind speed measurement, we can make an estimate based on our knowledge in the area. So if you know in your area, for example, we have light wind, this means less than 1 meter per second, or light to moderate, this means will be between 1 and 3 meters per second, moderate to strong 3 to 5 meters per second, and strong wind more than 5. So we need to find at least general description, then we can assume certain wind speed. So what I want to say here, still, if I don't have relative humidity, I don't have incoming solar radiation, I don't have wind speed, we still can use Penman-Monteith. So the minimum data requirement for Penman-Monteith is minimum temperature and maximum temperature. This is the minimum data. This is the minimum measurement you need in order to apply Penman-Monteith. I mean, in 56, they said, I mean, to use this approximate method, it will be better than using another equation to estimate ET node. So in AquaCrop, they give you this flexibility. They give you the option when you have all parameter needed for Penman-Monteith, and if you don't have all parameter, if you have only Tmax and Tmin, AquaCrop will calculate ET0 using this approximate method I just mentioned. So let's say how actual, I was talking about reference evapotranspiration, but how actual evapotranspiration is calculated in AquaCrop model. AquaCrop model is rely very much on what we call the green canopy cover. In crop what as they use leaf area index. Here in AquaCrop they use the green canopy cover and we refer to this as CC, crop canopy cover, CC canopy cover. And the definition of canopy cover is a soil surface covered by green canopy divided by unit ground surface area. So is area by area covered by the crop to total area. So if you look to this, I mean, this is the shadow of the crop. So the area of the shadow of the plant divided by the whole area. So this percentage, this is what we refer as the canopy cover. And all the calculation in AquaCrop is based on this ratio. And we see this not difficult to measure. And usually this ratio is between 0% when we plant when we seed, we have the seed in the soil. We don't have any cover, and could reach, not always, could reach to 100% at maturity. I mean, this ratio, when the whole soil covered by the crop completely, this ratio will be 100%. And usually this very easy, and this big advantage of AquaCrop. We all talk about how difficult to have the crop coefficient. The crop cover, I mean, now with mobile phone, we can take picture during different growing period of the crop. And from analyzing this picture, we can find the value of a crop cover. There's different software you can have on your mobile. When you take the picture directly from the picture, we'll analyze the picture and give you this ratio. So, for example, here we have CC 90%, we have cover. Here 80%, I mean, so we take percentage. At the beginning will be small, then will increase with the growing advance of the crop. So if we draw the relation between time from planting until harvesting and the CC, we see, I mean, the red is this, the crop cover curve. So start from 0 and will increase as the plant grow. And we can see this similar to crop coefficient, is similar in shape to crop coefficient. So it starts increasing, then at the end of, close to harvesting will start to decrease until harvesting will be 0. So the crop cover, this is the main thing used by AquaCrop to do all calculation. So how evapotranspiration calculated in AquaCrop? I mean, as I mentioned yesterday, evapotranspiration calculated from this equation, Kc, crop coefficient time ET naught. In AquaCrop, ET is separated into crop transpiration, TR, and soil evaporation. So we separated transpiration from evaporation. Crop transpiration calculated using crop transpiration coefficient time ET naught, and soil evaporation calculated from soil water evaporation coefficient time ET naught. So in AquaCrop, we need ET naught. We need to calculate ET naught, and this is done using Penman-Monteith equation. But now we'll see how to find the crop transpiration coefficient and evaporation coefficient. So the crop transpiration coefficient is function of crop cover. As the crop cover increase, the crop transpiration coefficient will increase. And the crop evaporation, the soil water evaporation coefficient of 1 minus crop cover. So because when the crop cover increase, the evaporation will be decreased and the evaporation coefficient will decrease. Evaporation calculated from this equation, evaporation reduction, and this will depend on the soil moisture content, time 1 minus crop cover, time maximum soil evaporation coefficient, time ET naught. For transpiration, transpiration, as I mentioned, is equal to transpiration coefficient time ET0. The question is how we determine the transpiration coefficient. Transpiration coefficient is equal to the maximum crop transpiration maximum time crop cover. So for every crop, we define KC, one value for KC. It is referred to as maximum transpiration coefficient. And crop cover, we need to define this, and I mentioned how we can measure. So the crop coefficient value is changing during the growing season. So time, the maximum transpiration coefficient. So the result this will have the actual transpiration coefficient. So the transpiration coefficient is calculated based on the value of crop cover, which changes from one day to another day, and the value of maximum transpiration coefficient. You notice we have this CC star, not CC. We adjust the measured CC, we adjusted from this curve to get the CC star, and the reason for that, when we have the photo by mobile, we have the photo from the top only, but the transpiration occurs not only from the top of the plant, but also from the side. So we increase the value of CC to take this in consideration. For example, if CC was 0.5, with this correction will be about CC star will be 0.6. So KC TRX, this is crop coefficient for maximum crop transpiration. When the canopy cover is complete, this means when CC is equal to 1. For barley, for example, this KC, the maximum transpiration coefficient is equal to 1.1. For grass is equal to 1. For most crop, for cotton, potato, rice, soybean, sugar beet, sunflower, tomato, wheat, barley, sugarcane, the value of maximum transpiration coefficient is 1.1. So it has almost fixed value. This is the maximum during when the crop cover is complete and CC equal to 1. So on the top here, we have the crop cover curve. The crop cover curve. Of course, we adjusted to get CC star. Here on the bottom, we have the crop transpiration coefficient. And we get this curve. We get from CC curve multiplied by KC TR maximum transpiration coefficient, which I said is fixed for certain crop. So we multiply the value of CC with KCTRX, we get the transpiration coefficient for every day. So I mean so the transpiration is function of crop coefficient, crop cover, it is 0, and the maximum transpiration coefficient. So actually we don't use crop coefficient. We in AquaCrop, we rely mainly on crop cover, which is really very easy to measure during the growing season. You need only to take picture during different period of the growing season. Of course, we need to include stresses in the water. We have two in the soil. We have two types of stress. We have soil water stress and cold stress. So we have water stress factor when water is less than field capacity. As go below field capacity, stress started. So we need to have a stress factor. So the actual transpiration is equal to transpiration calculated without the stress times the stress factor. Transpiration is calculated by crop cover time maximum transpiration coefficient time ET0. This will be multiplied by stress factor to get the actual crop transpiration. We include also what we call the cold factor, because when temperature is reduced under certain value, the crop stop growing, and we need to include this as a stress factor. So this equation gives the transpiration value, actual transpiration, and we have the water stress factor, the cold stress, the crop cover, the maximum transpiration coefficient, and it is 0. So this equation gives me the actual transpiration value, actual crop transpiration. So we need it is 0. We need the maximum transpiration coefficient, and I said this fixed for each crop, and AquaCrop has default value for each crop. You can change, but there is default value. And we need the crop cover and the stress, the cold factor, cold stress factor, and the water stress factor. So this is the way the AquaCrop is calculate transpiration. Okay, so maybe I can give 5 minutes of question before I proceed to irrigation management.
Yes, we received a question. We asked him about the mechanism to estimate the crop coefficient using photographs. I thought that was a fascinating tool, and somebody commented about what software we can do to utilize this, as traditionally it is commonly done to estimate the crop coefficient from GIS.
No, we don't need there is. Let me just try to remember this, because I have it on my mobile. There is there is software. It's called Canopy. You can download for free, and there is version for Android. You can have it on your mobile, and there's version for PC. So I mean, you can take the picture, and Canopy will analyze and give you the ratio of crop cover directly. Did I answer the question? Or? So Canopy, very, very simple software, and is designed to give you the crop cover ratio. Okay.
Yes, Mr. Awad has a question again.
Marlene, in fact, it's very, very difficult to teach online because you cannot see the reaction. Usually when you are in the class, you can get reaction directly. Okay, somebody asking to how maybe I will pronounce.
Dr. Ihab, if you can post the link for the application.
Yeah, I will put it on here.
Yeah, please type the application in the chat.
Okay. You can see it in the chat?
Yes, thank you.
Okay. So this is very simple, but very good software. Actually, you can take fixed picture or video. And when you take video, it will average the value for CC from different area, from different area in the field. Okay. Do we have another question on the concept? Because this really, the concept completely different from crop what and other method. We don't use the crop coefficient. I like it because always we find difficulty in defining the crop coefficient. In this way, I mean, you can train anybody in the field, even farmer. I mean, I just ask the farmer to take the picture and send to me on WhatsApp, and I can analyze and get the crop cover. Okay.
We have another question from Mr. Awad from Sudan again.
Okay.
Yes, thank you so much. So for me personally, I didn't use AquaCrop before, so I'm asking about the different purposes that or the scope of the AquaCrop itself and the different purposes that we might use the AquaCrop for. Thank you so much.
Okay. Today we'll see how we can use AquaCrop for irrigation scheduling and how we relate the crop yield to amount of water available in the road zone. I mean, AquaCrop relate directly the crop yield to the water available in the road zone. So this is the main use of AquaCrop. We can have different scenario for different irrigation schedule. We can have different scenario for deficit irrigation, and without going to the field and doing a lot of field experiment, we can have, for example, if we reduce the irrigation by 20%, how this will affect the yield, or 30%, how this. So it's a very good tool, but always we need to do calibration. I mean, it's better to have calibration, then we can use AquaCrop for irrigation management. And also we used one other use for AquaCrop, as I mentioned yesterday, is one of the tool it can be used to assess the impact of a climate change on the crop yield and the crop water requirement and the length of a growing season.
Thank you so much.
The question, can we take crop coefficient more than 1.1? Yes, we can. I mean, we can. There is default value for different crop in AquaCrop for maximum transpiration coefficient, but also you can modify this value if you know, I mean, better value than the one in the default. So you can change it, yes. In AquaCrop, there is parameter I mean, we changed from one crop to another crop, from soil to soil. And there is another parameter, it's called conservative parameter. Conservative parameter, usually this for certain crop is fixed, is not dependent on the area, but also you can adjust. But usually we don't adjust unless we are sure, I mean, there's different. But conservative value does not, this parameter is not changing from one place to another place. Okay.
Are there any further questions from participants? It looks like no. Please proceed.
Okay, let me proceed. So now I will explain how we use AquaCrop for irrigation management. In AquaCrop could be used for rain-fed crop, no irrigation during the season. This option available. Can be used to determine the net irrigation water requirement. Can be used for irrigation to evaluate certain irrigation schedule. This means if I already have irrigation schedule, I can just input this schedule and see how much the yield will be for this schedule. And I can use it to generate irrigation schedule depend on certain criteria. Generation of irrigation schedule mean, I mean, the AquaCrop will define when to irrigate and how much water to apply in every irrigation event. In AquaCrop, we'll ask you which irrigation method to use, and actually, this is a question nothing to do with irrigation efficiency. This is a question the AquaCrop need to know how much the percentage of the field, what's the percentage of the field covered by water, because evaporation will change depend on this ratio. For example, in sprinkler irrigation, this method, the whole field, 100% of the field will be covered with water. In the drip, only small percentage of the field will be covered by water. So evaporation from the dry part of the soil will be very small, while will be high from the wet. In field irrigation, also only percentage of the field will be covered by water. So an AquaCrop asks you for the irrigation method just to know what percentage of the field covered by water. In basin, maybe most of the soil will be covered by water. So in the default value, you can change this default. So this is the irrigation method. For a sprinkler, he assumes the soil surface, the wetted soil surface 100%. For surface irrigation, for basin 100%. For border 100%. For furrow irrigation, depend on the furrow, it will be between 30 and 100%. For drip, will be between 15 to 40. Subsurface is 0. So here you can input, I mean, you have this default value, but you can change it. I mean, if you have, you are sure this not represent the actual value. So we need to know the irrigation method just to know what the percentage of the weighted soil surface. So this is the option: sprinkler, surface, basin, border, furrow, and drip irrigation. So AquaCrop allow to evaluate certain irrigation schedule. So let's say, I mean, you are in the field and the farmer following certain irrigation schedule, and you need to evaluate, is this irrigation schedule is good or not, and how the yield in the field based on this irrigation schedule. So in this case, you need to input the amount of each event, irrigation event, how many millimeter, and the date. So this very good advantage of AquaCrop, because you can input and you can try different irrigation schedule. So we need to specify for each irrigation event the date and the net amount of water applied, and if we know the EC of the water, salt content. So this screen, this is the one we need to input. We need to have the date of the irrigation event and the net application, how much water we apply in one irrigation. So we input the actual. So in this case, not AquaCrop determines the irrigation schedule. Here we are inputting irrigation schedule based on the practice in the field, and we can evaluate this schedule. You can see here it said net application. AquaCrop always, in irrigation, always only work with net application. Even all anything related to irrigation is net, not the gross application. This is very important. So if you calculate how much irrigation you need to apply, this will be net. You need to know the irrigation efficiency in order to get your gross irrigation amount. This is very important, you need to know. And of course, here you can input the value of EC. If you know the quality of your irrigation water, the salinity, you can enter the value here. So this number here, this is the number of days after sowing, I mean, after the planting date. Here, I mean, we plot the irrigation event. I mean, this is the sowing date. And this is the irrigation event based on the schedule we enter to the AquaCrop. So we have here one event 40 millimeter after 15 days, 45 millimeter after 32 days, and then we have equal event 45 millimeter. Okay, before I proceed, let me try to run AquaCrop. Of course, you can download AquaCrop. You can download from FAO website. Just type on Google, I mean, AquaCrop download. This is free. You can download, and there is a lot of documentation, and there is a lot of video, demonstration video. It helps you to learn about AquaCrop. So I click on the icon. I will start AquaCrop. You can see, Marlene?
Yes, we see your screen.
Okay. I click on the start. Okay. And this is the main window of AquaCrop. So here we input the climate data. Here we input the crop data. Here we input the irrigation data, field management data, soil data, groundwater data. And here we have the initial condition. And let me go through an example. So for climate, we already prepare climate file because it takes time. I'm running example from Jenin, Palestine on potato crop. So I select my climate file. Let me show you what data included in this file. So we have the rainfall, and in AquaCrop, we need daily value for rainfall. Definitely we need daily value for rainfall. We cannot use monthly or yearly. So we need to input the daily value.
Excuse me, Dr. Ihab, we're currently still seeing your file folder structure. We're not seeing the software, the model itself.
I don't know. So what you are seeing now?
We see your Explorer, the files, the AquaCrop files in the folders. We're not seeing the model.
Yeah, I don't know. Let me see. I don't know why.
Maybe close the file and then make sure you're.
Yeah, thank you for letting me know. Yeah, therefore I asked if you see it was different screen. So now you see the AquaCrop model? Marlene?
Oh, waiting for it to come up. It's not showing quite yet. But it looks like something's coming.
Okay. Cross your finger.
It doesn't appear to be coming up.
Oh.
And maybe it's too hard to share or something because it's just a black screen that is showing.
Let me see if I changed. Nothing changed now?
No, nothing. Still
Can
a
we
black
ask
screen.
the other participants the same? You see only black?
We only see black.
Yes.
I don't know.
If it has a video component, Dr. Hab, sometimes MS Teams can't handle that. So it's sometimes, if it's an animation component, sometimes it blocks on Teams. It's too heavy.
Yeah, no, I have some IT, maybe they need to help me. But because it's very important, because a lot of I will show a lot of examples of running AquaCrop. So we need to solve this problem. Yeah, when I share my screen, AquaCrop is not option here. Can you give me 1 minute just to consult our IT?
I think it's a challenge with Teams. I don't think it's an IT problem. Perhaps you have screenshots on your presentation.
Yeah, but it was better to.
I know, but it's a challenge. Applications are difficult on Microsoft Teams, so we'll need to proceed with the presentation, and maybe before the start of next session, we can share other screenshots that may have been missed.
Yeah. Okay. So. Okay. Anyway, so I mean, what important, I mean, so, I mean, just let me summarize this. I mean, so this option, I mean, very powerful because, I mean, you can try different scenario for irrigation. This is not perfect full irrigation. You can just assume different date for irrigation and for a different irrigation amount and see how this will affect the yield of the crop. So this option available at AquaCrop. The other option is generation of irrigation schedule. This means this will give you the optimal irrigation schedule based on criteria I will talk about, and this, if you use this, will give you the irrigation schedule with no water stress. Always will be based on the criteria, will be close to the field capacity. So the AquaCrop will have the schedule based on time criteria and on depth criteria, how much to apply. Of course, the criteria does not have to be fixed for the whole growing season. You can change the criteria for different growing stage. And as I mentioned at the beginning, very beginning today, when I explained the concept of irrigation, just a minute. Okay, so I said the irrigation water will be between field capacity and wilting point, and the moisture between wilting point and field capacity, this is what we refer to as total available water. So I mentioned that our moisture should be always higher than the critical soil moisture content. The critical soil moisture content is somewhere between wilting point and field capacity. So this is the allowable root zone depletion. This percentage of total available water. And this we refer to as readily available water. So this is the readily available water. In AquaCrop, ask you to select the percentage of readily available water you allow to the plant to consume before you refill the soil profile back to field capacity. So just we have the total available water, this between wilting point, and field capacity. We have the readily available water I was talking, which is percentage of total available water. And usually we allow plant to consume percentage of readily available water, maybe the whole readily available water or only small part of it. So the percentage I need to input is percentage from readily available water. And the percentage of readily available water from total available water is fixed in AquaCrop and equal to 0.5. So percentage of readily available water from total available water is fixed in AquaCrop and equal to 0.5. So if I allow 0%, this means always I will be at the field capacity. If the ratio, I put 100%, so this means I allow the plant to consume the whole readily available water when I put 100%. I have another option. I can input fixed interval, and in real life we face this sometime. I mean, the water is available only in fixed date every 7 days or 10 days. So AquaCrop gives you this option to have fixed date between irrigation interval, but this interval should be always less than the maximum irrigation interval I showed at the beginning. And another option, especially when we have rice, and we know that when we plant rice, we should have always water depths in the field. So we put the depths, we need to irrigate when the depths drop below certain value, then we have to irrigate again. So we put the minimum level of water, then the AquaCrop can initiate another irrigation. So let me talk, we need two criteria. Depth criteria, which define how much water to apply. So I mean, the first criteria defines the time when the plant consume percentage of readily available water, then this means I know that I need to irrigate at this time. But how much water I need to apply, I have option here. If I choose back to field capacity, so I need to add amount of water to make the soil moisture again at field capacity. Or I can input fixed application dose, certain amount, I put it as fixed value, and this will be fixed irrigation value for this option. So this screenshot from AquaCrop for time criteria, this is the option. We have fixed interval, so I can say I need to irrigate every 7 days or 10 days, depend on the water availability. Or I have another option, allowable depletion. This is a percent, this allowable depletion from readily available water, and this in unit in millimeter, or allowable depletion as percentage of readily available water. I put percentage, or for rice, we put the water layer between bond and how much the minimum depth allowed in the field. So this option, I select one of them to define the time of irrigation. Let me explain more. If I put the allowable depletion is 50%, this means the AquaCrop calculates the water balance every day. When the plant consumes 50% of readily available water, this means this is the time for irrigation. So this criteria defines the time of irrigation. Based on the percentage, I put it here and allowed for depletion. When 50%, for example, of readily available water is consumed from the available water in the soil, from total, this percentage is consumed. This means now is the time for irrigation. But how much water need to apply at this time? This we define the depth criteria. If I said back to field capacity, so we need to add an amount of water to increase the soil moisture from this soil moisture at, when I consume this percentage of readily available water until I get back to field capacity. So the time criteria defines the time of irrigation, and the depth criteria define the amount of irrigation. So using these two criteria, we can have full irrigation schedule, and we'll have exactly how many irrigation events we have and the time for every irrigation event and the amount of each irrigation event. So this example in AquaCrop, we put, this is the day of from growing season. This is the time criteria. I select allowable depletion, 50% of readily available water. Then if I put 0 here, this means I select back to field capacity, and here I have the quality of water. This, it was for 22nd of March. I can change the criteria during the growing season. So the first criteria is valid until 25th of May. Then here I change the criteria to 100% of readily available water. So I allow the plant to consume 100% of irrigation of readily available water before I irrigate again. And I put 0 here. This means I will add water to go back to the field capacity. So we see this picture. Here we see the irrigation event. So the first criteria was valid from day 1 to day 65, when we allow 50% of readily available water. So we have small irrigation event. Then we change the criteria at day 65. So we allow the plant to consume 100%. So we have larger irrigation. Always we go back to the field capacity. This line is the field capacity. We can ask AquaCrop to show the irrigation schedule, I mean the date for different irrigation event and the amount. This amount and this the date. So we have irrigation, we can either plot or table with irrigation event. We can have criteria. We can select fixed interval and fixed net application. So always we apply 35 mm in all event, and we apply every 7 days. So we can see here is fixed interval 7 days and fixed application value for the irrigation. I guess I will, for now, I will stop here because time, I guess we took some time from, if you have a question, then we can go to the break.
Yes, we have one question on how we can integrate the use of soil tension when we have the sensors in the field with this scheduling method.
Yes, yeah, this, we need to do what we call real-time irrigation scheduling. So for example, if we have tensiometer in the field or TDR in the field, and we should define before at what reading for tensiometer or for TDR we need to irrigate. So every day input the weather data to the AquaCrop, and when the soil moisture at the tensiometer indicates that I need to irrigate, then we add irrigation event in AquaCrop. So in case we need to integrate, we have to do real-time simulation. And we can do calibration because we'll get the soil moisture from the instrument, TDR or tensiometer, and we'll get the moisture from AquaCrop. So maybe we need to adjust some parameter to make them match.
Thank you. Are there any other questions from the participants?
Sorry, I mean, if it was a lot of information, usually, I mean, we have 1 week for this, but it's good to introduce it to you. And as I mentioned, there is a lot of document on the website, AquaCrop. When you get the principle, it will be easy for you to follow with the document on AquaCrop site.
Thank you so much for that lovely presentation. It was very enjoyable, and we look forward to the next session, which will encompass deficit irrigation and supplemental irrigation. The next session will commence in 1 hour at 12:30 Cairo time. I encourage, for those of you who have not participated in our survey, to please do. We've received 27 responses thus far. Thank you so much. We look forward to seeing all of you back in 1 hour. I will close the survey in 15 minutes for those who have not responded. Thank you.